me for this for the UNIFI consortium. So today's I'm going to talk about your grid forming concepts for offshore wind power hubs connected through multiple HVDC links. And this is one of the new challenges that we are facing these days, especially in Europe and some in US too, like being planned. So, and I'm going to share our experience with some of the projects that we are involving as well. So this is the table of content. So I will start with requirements for grid forming converters and then talk about the offshore HVDC grids and the dynamic performance of the offshore grids and the requirements for the grid forming converters and the challenges. And then some of the control concepts that we tested for one of the projects being planned in Europe right now. It's the North Sea Wind Power Hub project, and some of the test results and the summary at the end. So let me start with the requirements for grid forming converters. This is mainly a recap. You may also familiar with this, but I just wanted to highlight some of the requirements that we want to mainly discuss in any of the projects. So let's start with the voltage support, especially this voltage support is common for both grid forming and grid following. And when we talk about voltage support, we expect fast voltage recovery, especially when we have many the power electronic devices in the system. We want to have fast voltage recovery to keep the stability of the system. So for this, like, you know, that when we have synchronous machines in the system, we have the fault currents right now, like when we don't have synchronous generators, conventional generators in the system, we don't have a lot of fault current contribution. And any of these devices, the current contribution would be close to 1 per unit. So, but somehow, like if we can manage this current in a way that the converter can quickly recover, that is the objective here. So as part of this, like we usually use the reactive current prioritization logics. You can see in this diagram that basically when the current is above 1 per unit, like whatever the maximum current, you can reduce the active current temporarily and allow reactive current to increase in order to get the voltage recovered. Because without having voltage recovery, there's no point of even talking about power frequency stability. We have to have voltage recovered. So that is the priority here. And then in addition to that, we need the steady state reactive power support. And this is very common, like we need the PQ capabilities based on the grid code requirements and so on. And in order to decide these requirements, we have to do proper studies, especially if you have a lot of inverter-based resources in the system, especially the load characteristics would be really important to be considered, because let's say if you consider linear loads like RLC loads, you may be able to recover the system with 1 per unit of current injection. But let's say if you have a lot of induction motors and so on, nonlinear loads, you may need higher current ratings for the converters. So these are the things that we have to first understand based on the system. And this understanding should be achieved through proper system studies. And then the next support that we need is the frequency, power frequency support. And so I'm going to talk about the well-known 3 regimes. The first one is the inertia support. So here, when we talk about inertia support, right away we expect for the converter to be behave like a synchronous generator. So basically, we expect the power to be adjusted based on the rate of change of frequency and the frequency deviation. So this is actually, this objective can be achieved even from a grid following converter. So if you have a proper frequency controller, but most important thing in terms of the inertia from a converter that we expect to achieve is the inertia support during a disturbance and at the recovery. And you know that if you have a fault at a terminal of a synchronous generator, the energy is accumulated in the mechanical system, and when the fault is cleared, we see that there is a significant amount of active power injected into the system. So this is very important when we have nonlinear loads. And again, like if you have a lot of induction motors and so on, they need a power boost for them to recover quickly. And this is something that we cannot really achieve with today's converters because of the current limits that we have and the energy handling limitations. So especially when we move forward with grid forming converters, this is something that we have to consider, how to handle this excess energy and how to release energy when we need. So that need to be decided, especially like we need equipment for this purpose, like battery storage or get the energy from the DC side quickly and so and so. And in addition to that, we need the controllers. It is well known, like grid forming controllers can help with these requirements. Basically, the control is set up such a way that we provide the energy based on whatever the requirements, like based on grid forming concept defined in the controllers. But most important thing is not just the controllers. Controllers won't play a role other than giving the orders to get that whatever the power they want, but that power should come from somewhere. Like we need equipment and equipment ratings. This is the most important thing, and always we forget this point actually. So we have to be very careful with defining grid forming requirements in both together with control requirements and the equipment requirements. So I will move forward. So then the second regime of frequency control is the primary frequency control. And this is the govern action, similar to a synchronous generator. Like we need the govern action to be simulated with the grid forming converter as well. And the most popular technique is to use the frequency group control. And again, like in addition to the control, we need the equipment support to get the required energy for this the primary frequency control. And so for this purpose, like in order to get this energy, we have to either add energy storage or we have to underutilize the energy sources. For example, like we may have to operate wind and solar at a lower power level than available power in order to get the whatever the reserves, that just to keep the reserves that we want, similar to conventional generators that we do right now. And then the third regime is the secondary frequency control. This is the AGC support, area generator control support. And basically, if the system operator is asking.
Hey, Chandana, sorry to interrupt here. It looks like your slide isn't advancing. Can you toggle your screen share off and then back on, please?
Okay.
Okay.
Brian, can you see it properly?
Yeah, okay. Yeah, all right. Okay, I think we're fine now. All right, thanks. Please proceed.
Okay, sure. Thank you. So then, yeah, I was talking about the secondary frequency control. So basically, we need the power levels to be adjusted based on the the system controller, AGC controller request. So that is the third regime. Is it good now, Brian? I hope that you can see the new slide. So that
Yes,
is
everything is good.
yeah, thank you. So yeah, now I'm going to talk about the offshore HVDC grids. So in like we have to keep in mind these voltage support and frequency support requirements. And let's talk about the HVDC grids and their characteristics, and then how to get these voltage and frequency support for the offshore grids. So before going into that, like I would like to introduce this the offshore multi-terminal offshore system considered for the new North Sea Wind Power Hub project, and they call it this as AC hub configuration. So in this case, like we have two HVDC bipoles, HVDC 1 and HVDC 2. HVDC 1, HVDC 2 connected together from the AC side, and this is a single bus connecting both of the HVDC bipoles. In terms of converters, we have 4 converters: positive pole converter of HVDC 1, negative pole converter, again like similarly HVDC 2, and all the wind farms are connected together to the same AC bus. Actually, there are bus couplers and other things here. I am not showing the details, but in general, all the wind farms are connected to the same node. So that is the typical arrangement of the offshore HVDC grid. So that means all these converters are tightly coupled. So now the objective of this, like basically we want to regulate the voltage and frequency of this offshore AC grid with all these HVDC converters connected together and the wind generators connected into the same node. So the basically we expect the HVDC to transmit whatever the power coming from the wind farms while maintaining the stability. And so the one of the main challenges is the bipolar HVDC systems in parallel to deliver this the power coming from the wind farms. Like when you connect multiple grid forming converters in parallel, you can think about like what kind of issues that we can face here. So what are the dynamic characteristics of this offshore grid? Like when we talk about the inertia, now you know that we are talking about a zero inertia system, no inertia at all. And we have some inertia in the wind turbines, but most of the wind farms right now used in offshore are type 4. So that means whatever the mechanical characteristics of the wind farms are decoupled from the grid from using back-to-back converter. So that means like no inertia at all. And since we don't have any mechanical characteristics here, actually we don't have to really work on the swing characteristics that we use for the synchronous generators. We can use something else. So that is actually one of the advantages of offshore grids. I will explain about that bit later. And then second challenge, the second dynamic characteristics is that that all the power coming from the wind farms are connected to the same node, and this power output is regulated by the power plant control of the wind farms. Basically, for the HVDC, it's like multiple constant power sources connected together. When I'm talking about the steady state performance, during the steady state, like it's like constant P, multiple constant P sources connected together. So So that means the HVDC should be designed to absorb whatever this power coming from the wind farms without knowing like, okay, what would be the power? Like we have some kind of idea like based on the dispatch levels, but like basically this dispatch level is regulated by the wind turbines, not the HVDCs. And then the other issue is, that when now we have constant power sources connected to the grid forming converters, uh, if we have some conventional load, they are providing kind of damping. Like let's say if the frequency goes down, the loads may go down and come back, and there would and if the voltage changes, the load may change. Now we don't have any of these loads in this system. So basically we have power sources, and the HVDCs to transfer that power to other locations. So that means we have lack of damping in this system. So actually for the HVDC, it's a big challenge to maintain the power balance in this very stiff system. So we evaluated these challenges for the North Sea Wind Power Hub project, and some of the challenges that we observed. So I will go through the challenges that we faced. The first thing that we observed, like if we consider one HVDC system, so that means a bipole HVDC system, that means like we have positive pole converter and the negative pole converter, you can see here, they are connected together from the AC side. So this one is grid forming and this one is also grid forming. So what we observed that as soon as these two are connected together from the AC side, they both start fighting. So I will explain the reasons a bit later. So this is one mode of interaction that we observe. The two converters of the same HVDC systems can interact heavily. Actually, without making any controller modifications, we couldn't make this working actually. So I will come into that bit later. So the next interaction that we observed, the interaction between multiple HVDC systems. We have this HVDC system. This is the bipole, first bipole, and the second bipole connected together. When we connect them, there was a bus coupler here. As soon as the bus coupler is closed, you see that huge interaction between the two systems. Again, it's very hard to keep them stable. So what are the reasons for these challenges, the interactions? So one thing that we observed that, that when we talk about a grid forming converter, so basically the controller is determining, it's a voltage source controller. So basically controller will determine what would be the voltage magnitude and angle, internal voltage magnitude and the angle. So if you inject this into the converter will create the voltage based on the voltage reference coming from the controllers. Converter will create the sine wave. But now the thing is, in a modular multi-level VSC converter, we have submodules connected together in the converter. So from the references, it has to create this sine wave. There would be some little deviations, and because of that, there might be high frequency harmonics as well. But in addition to that, the converter has to keep the power balance between the submodules. So that means we observe that this power balancing logics in the submodules can interact with the voltage reference coming from the converter. So at the end, like we give a reference to the converter, but converter is not giving the voltage output the same. There might be slight variations, and those variations are good enough to create interactions between the converters in the same pole, same HVDC system, two converters. So the other thing, like we always try to control the voltage magnitude, is to control the point of connection voltage. So basically to control the reactive power output. And then the angle is controlled to keep the power balance, basically get the power, whatever the power coming from the wind farms. But we know that these two are coupled together, and because of this coupling, we observed that there are so many interactions can happen between these devices. So those are the challenges with especially like defining the references. And then the other challenge that we observed, these two systems are tightly coupled actually. For example, if we consider one HVDC system, we have this converter transformer, maybe about 10% impedance. And then there might be some, there are phase reactors here, maybe introduce another 5.05% impedance. Altogether, it's about 5% impedance. So altogether, maybe about 15% impedance in the converter. So when we talk about synchronous generators connected in parallel, like even the subtransient impedance is about 20%, and with the transformer impedance, it's about 30%. But when we talk about the steady state impedances, so in a synchronous generator, it's quite big, like it's more than 1 per unit in most of the cases. So that means like we are dealing with very small impedance here. So, and again, to keep the converters running is quite challenging because of this very small impedance. And again, like when we talk about two HVDC systems, actually the impedance is almost like nothing. There's no impedance, it's just the bus coupler, right? So, and because of this, like keeping this, like keep them running stably is quite challenging. So actually, before coming into this slide, I want to mention a few things that actually for the North Sea Wind Power Hub project, we considered many grid forming concepts available in the literature. And for example, virtual synchronous machine-based controllers and some transient control mechanisms available in the literature, but we had a lot of issues with these actually to get them running because of these interactions, these tightly coupled converters. So at the end, like we had to come up with something new actually. So in order to keep them running under all conditions, like under steady state conditions and the transient conditions. So basically to maintain the small signal stability, transient stability, and all these stability requirements, in order to satisfy all these requirements, we had to introduce new grid forming concept for the offshore HVDC systems. So I will explain a little bit about in a very high level. I'm not going into very details, like, but the concept that we were testing, and again, like this, there might be many other techniques available. This is something that we came up with. But so again, like for example, virtual synchronous machine technique may be possible to be used with some modifications. But again, like when you design that, you have to consider the possibility of all these interactions. That's the most important thing. And then, yeah, let's get into what we did actually. So this is what we came up with. Actually, we introduced a master controller to regulate the power balance between the converters. Basically, the master controller will look at the power references coming from the dispatch center, and then the power outputs of each converter. And based on that, like based on the droop characteristics, it will define what would be the frequency error for each converter. So this is the purpose of the master controller, to regulate the offshore frequency, and then each pole had its own grid forming controls in it. So each pole level control includes the internal voltage. Hello. So I'm hearing some background noise.
I'll see if I can find the source of that and mute it.
Okay, sure, Brian, thank you. So basically, the pole level grid forming controllers define the internal voltage magnitude and angle for the converters, and we had to introduce some special controls at pole level in order to keep the stability of the system. I will show you a high level block diagram what we did. Like, so this is the pole level control concept that we used. Let's talk about the calculation of the angle. We have basically, if you have the frequency, you can have a oscillator to determine the angle. Basically, you can integrate the frequency to get the angle. So this frequency was coming from a frequency droop control. So that is similar to any grid forming control concept. Like, you can use a control mechanism similar to a governor control to determine the frequency droop. And but we didn't use the swing equations in these controls. Basically, from the frequency droop, we determine the frequency. But what we specially introduced was the transient angle control. Basically, for the offshore system, frequency is just for steady state purposes, just to keep the power balance between the converters. Mainly during the transients, you know that if we have a voltage source, if you know, if you can quickly change the angle, you can keep the power balance even for a 60 Hz signal without changing the frequency. So that was the concept that we used. Instead of changing the frequency, we change the angle directly using a transient angle controller. So, and yeah, this is the main ingredient for the quick control to maintain the stability during the transients. So, and then when we talk about the voltage controller, as in the conventional systems, we use the AC voltage controller. So that means the point of connection AC voltage was controlled by the HVDCs together with the reactive power droop. So that means like we can keep all the parallel converters working together with the droop. And then with any other grid forming converter, we need the current limiting controller. This is very important. Like, you can go for different kind of current limiting logics. For example, you can introduce virtual impedances to limit the current. At the same way, you can use a separate controller to limit the current. So in our case, we used a separate controller to limit the current during the transients. And I talk about the interactions. So when I talk about this earlier, I told you that the interactions can happen between the two converters of the same HVDC system, and the interactions can happen between multiple HVDC systems. So in order to control any interactions between the converters in the same HVDC systems, so we introduce a pole circulation current control. Basically, we measured the current error between the two converters and tried to control it to 0. So it worked quite well, and you can even control during energization, during transients, and you can easily connect the two converters together. You can synchronize the converters easily because of this additional controller. And then, as I explained earlier, the interactions can happen between the two HVDC systems in order to damp out any interactions, oscillations between the two systems. We observed so many interactions between the two systems, like two HVDC systems, both in active power and reactive power. Because of that, we had to introduce two different damping control loops for both D-axis and Q-axis to damp out the oscillations, both in active power and reactive power. So basically, with all these modifications, you can see the additional controllers that we introduce here, like in yellow, orange, and then at the end, like we determine what would be the internal voltage magnitude and the angle. So with all these modified controllers. So, and now I will show you some of the results that we obtained for very critical and extreme faults. Like for example, here, like I'm showing, we applied a 3-phase to ground fault at the offshore point of connection bus, and then the fault was cleared by tripping some of the wind farms. We tripped 500 megawatt of wind generation in the system. In this system, actually the total generation is 4,000. So that means we basically tripped 25% of the wind generation to clear the fault. And I will show you some of the results that we obtained in EMT simulations for this system. So yeah, here are the results for the two HVDC systems. You can see, so this is how the voltage recover. And this is the frequency deviation. You can see there is some frequency deviation, and the frequency nadir and the frequency, the rate of change of frequency here, like it's all the converters work together. And again, like about this frequency drop and so and so, we use 5% frequency group. If you use a smaller frequency group, you can get this frequency even higher than 40. Here, this is a 50 hertz system, higher than 49 hertz. And about the active power sharing, you can see that the active power is like you don't see any deviations of the 4 HVDC converters shown here. Like we have 1, 2, 3, 4 converters. So all the HVDC converters work together. So there's no fighting at all. This is the reactive power for the same disturbance. So you can see that there is some deviation during the transients. We are talking about 2-second duration here. During this 2 second, you can see some small deviation between HVDC system 1 and 2. But other than that, the reactive power balance is quite good as well. And then I told you that we tripped 500 megawatt of wind generation in this case. You can see the power is distributed among the converters based on the group. And the second disturbance that I want to show you, like it's a DC fault. So we applied a DC fault in one of the DC cables here in this pole. And then you know that if when these are half bridge converters, by the way. So in order to clear these half bridge, like the DC poles in half bridge converters, we have to basically trip the converters, because we don't have DC breakers here. So basically, we trip this converter after when we clear the fault, and then now there is a power balance. wind farms are generating more power, but we don't have enough converters to transfer that power. So that means we have to either trip the wind generators, or like you can fast ramp down uh, wind generators. Actually, we look at multiple choices. Like uh, the easiest way was to trip the generation, but the client wanted to evaluate the possibility of keeping the wind farm running as well. So then, because of that, we considered as the second choice, we considered fast um, power ramp down of wind farms. Actually, we could achieve that if we can get the power ramp down within about, like, let's say 4 seconds. But even that, it's a little bit challenging to achieve. And other possibilities, having a chopper here, like you can see that there are DC choppers here in this system. So what we can do, like we can move these DC choppers to the AC side as an AC chopper. So basically we can use that AC chopper to the dissipate power during the transients, and then we can slowly ramp down the wind farms. And these are multiple options that we have, but at the same time, like what we have to basically do, like we have to somehow reduce the wind generation to keep the power balance. So I will show you the results with wind farm tripping. So basically, now when we don't have one of the converters, we have to trip 1 gigawatt of wind farms. So this is how the system looks like for the wind farm tripping. For the HVDC um, disturbance, you can see this the orange one is the one the converter trip. The other three are shown here. Like you can see that there are some frequency differences between the two HVDC systems. Actually, we are here we are plotting the converter internal frequencies, and there might be differences, but at the point of common bus, it's the same frequency. When we look at the power balance, so this is the one tripped. We don't have to look at that one. You can see other converters. The converters in the same HVDC systems are okay, but there are some differences in the converter in the one with the fault, but they quickly come into the same level. So at the end, like there's no deviation. So, and the reactive power only during the transients there are some deviations, but at steady state it's the same deviation. And this one is the trip one. You don't have to look at that one. It's that results is junk. So yeah, that's how the system responds. Like in order to get this performance, we had to have certain requirements in the HVDCs. One thing is the current rating. In order to maintain this power balance, like we had to have a little bit higher current rating for the converters. This is the main requirement with the grid forming converters. So we had to increase the transient current rating for 1.3 per unit. So usually, like a typical converter has about 1.1 per unit transient current rating. So we had to increase it another 20% to about 1.3 per unit for a very short duration. So it's a maximum less than 1 second duration. So, but when we talk about the IGBTs, it's almost like a steady state. So, yeah. So just to summarize what I was talking about today. So basically, grid forming converters of offshore systems has unique challenges compared to the onshore grid forming applications. But the thing is, these challenges, even for onshore systems, we have to face these challenges in the future because the way that the power system is growing right now. So we will see that multiple converters connected together, and the AC system is very weak, and the most of the loads would be power electronics based on that. Like we may have to face the same challenges in the future as for the onshore applications as well. So based on this experience, actually we highly recommend for utilities and TSOs to ask the converter manufacturers even now to demonstrate, just to demonstrate their grid forming concepts with multiple devices connected to the same node. So this is very important actually. Like they may have like very sophisticated grid forming concepts, but the thing is, like if you put multiple devices together, will it work? That is the question that we have to answer, and that was really important, like from our experience. So with that, I will finish this presentation and open for the questions.
All right, thank